Okay, I'm talking about a situation here where somebody goes in for surgery. Okay, kind of mimics an experience I had about 13 years ago, but a little more extreme. Okay, so we're going to look at physical condition versus number of weeks after surgery. Okay, we're going to say that 8 weeks after surgery, my physical condition is 40%. That's what this point means. And after 12 weeks, then my physical condition was up to 60%, 100% being the maximum condition I could maintain, 80% being what I was probably maintaining before the surgery. Okay? So these numbers would have actually been a little higher in my case, but this would not be atypical for somebody who had major surgery. Okay? Mine wasn't as major as some, so it wasn't semi-major. So this is not a personal situation because, it's a situation that people do experience when they go into surgery, especially for major surgery. All right, now, what we want is a mathematical model of how my physical condition would progress or how a person's physical condition would progress. And we're going to assume that that person is, by 8 weeks, active enough to progressively build back up. Instead of trying to model with these points on this graph, I'm going to make it a little simpler and a little more accessible by saying, okay, at this point, I was 60% below peak, 60% below potential, okay? At 40%, I was 60% below my 100% level. So I'm going to say I'm down 60% at x equals 8. And then when we're at 60%, we're down 40%. So we're down 40% at x equals 12. Now, if we do a new graph of y equals how far down versus x in weeks, then at 8 weeks, I have y equals 60%, and at 12 weeks, I have y equals 40%. So there are 2 points on this latest graph, 860, meaning 8 weeks, 60% down, and 1240, meaning at 12 weeks, I'm down 40%. And just for orientation on this graph, low is good, okay? If I'm 100% down, it means I'm dead, okay? And, something to be avoided, usually. So if I reach 0, that means I'm in peak physical condition, the best physical condition I can be in given my age and my physiology, okay? So I'm striving for 0. I don't have time to work out enough to hit 100%, okay? But I do have time to hit 80%, which is pretty good. Assume, these are just figures. They don't necessarily reflect me at that time, but there it is. Okay. Now, in order to model this, I'm going to assume that the better condition I get in, the harder I'm going to be able to work out. Okay. But no, I'm not going to assume that. I'm going to assume that the closer I get to my maximum, the harder it's going to be to improve. So I expect quick improvement early and then leveling off. And that's kind of an exponential, isn't it? So we would expect something like this. Here I am at 8 weeks. And now we expect the closer I get to 100%, the more slowly I'm going to progress. And that is pretty much the way things work. Whether it's an actual exponential or not, it does have that sort of And that's recovery from anything. You get a bad case of COVID, okay, or get a bad case of something that can kill you but doesn't. It's going to take you a period of weeks to build back. Okay, so anyhow, to start the model, we're going to assume exponential. This is an exponential model. So let's label it as such, exponential model. To start, we plug points into the form y equals ab to the x. Okay? Plug in 8, 60, and we get okay, let's say into y equals a times b to the x. We get 60 equals a times b to the 8th. Plug in the coordinates 12, 40, and you get 40 equals ab to the 12th. We have two equations, two unknowns. We encounter this when we're doing linear functions, where you have the form y equals mx plus b. If you have 2 points, you have an x and a y to plug in, and then you have another x and a y to plug in. You get two simultaneous equations. And we're going to be working on simultaneous equations shortly. When we did linear equations, those were simultaneous linear equations. So hopefully you remember having done that. These are not linear equations. These are not linear equations, but fortunately they're easy to solve. Okay, so we have 60 equals ab to the 8th. We have 40 equals ab to the 12th. We're going to call this first equation 1, second equation 2, just so I can refer to the equations. And then I'm going to say divide equation 2 by equation 1. Meaning you divide the left-hand side by the left-hand side, you divide the right-hand side by the right-hand side. You get 40 over 60 equals, AB to the 12th over AB to the 8th. Now, I'm going to ask everybody if you can simplify left-hand side into a fraction in lowest terms, and can you simplify the right-hand side? So see what you can do with those two equations, and I'll take a look, and then we'll see where to go from there. Okay, to simplify, again, we have 40 over 60 equals AB to the 12th over AB to the 8th. 40 and 60 have a common divisor of 20. If you divide 40 by 20, you get 2. If you divide 60 by 20, you get 3. It's 2/3. I think somebody got it 3/2, got it reversed. Right idea, though. Okay? Now, that's the same as A divided by A multiplied by B to the 12th divided by B to the 8th. What's A divided by A? Well, it's 1. What's B to the 12th over B to the 8th? That's B to the 12 minus A. Remember your rule for exponents. We'll call it, use X here. X to the A over X to the B equals X to the A minus B. Specifically, B to the 12th over B to the 8th equals B times B times B. 12 of them, right? Divided by 8 of them. I can write that as B times B times B times B over 1 multiplied by B times B times B times B times B times B. 8 of them divided by 8 of them. Okay? Which equals B times B times B times B over 1 multiplied by 1. And we can say 1 over 1. And that just equals B times B times B times B, which is B to the 4th. You should understand that. Obviously, you don't always want to write that out, but you can visualize it. So when you see B to the 12th over B to the 8th, you can visualize 12 B's in a row divided by 8 B's in a row. And you can group 8 of the 12 with the 8, make a 1, and leaves you 4 of them. Okay? And that's the same as, of course, finding B to the 12 minus 8, which is the rule, but there's a reason for the rule. So you really want to try to understand the reason for the rule, because at this point in a pre-calculus class, 80% of students will not know what to do with those exponents, okay? Take a little slam at our overall system, which I think is overall pretty good for permitting us to placement test people. Seems to me one of the more insane things people have done if your goal is to educate people, but we'll see. Okay, I'm sure there's a contrary argument because there's some good people that made that decision. B to the 4th equals 2/3. How do you solve B to the 4th equals 2/3? Well, I'm going to go over it. Make sure you understand this. There's another rule of exponents, which says x to the a raised to the b is x to the ab. And that can be written out similarly, but I'm not going to take the time here to do it. So make sure you know this rule and review and understand why it's so, because you're going to need these rules. Okay. The way we apply the rule here is we take b to the 4th and we raise it to the 1/4 power. And then, of course, we've taken the 1/4 power of the left-hand side. We take the 1/4 power of the right-hand side. And we get B to the 4 times 1/4 is 2/3 to the 1/4. That gives us B to the 1 equals 2/3 to the 1/4. So B is approximately equal. Okay, 2/3 to the 1/4 is 0.67 to the 1/4. 0.9 to the 4th power is about 0.65. So I'm going to say B is approximately 0.9. It might be 0.91. It's between 0.9 and 0.91, I think. You need to use your calculator to calculate it, just to see. Because I think my brain is working okay right now, but who am I to tell? Okay, so by manipulating this equation, dividing one equation by the other, we get B to the 4th equals 2/3. We take the 1/4 power of both sides and we get B is about 0.9. Did you get it? Did you calculate it? Just okay. So it turns out it was 0.9036, between 0.9 and 0.91. That was a pretty easy approximation. So it didn't take any genius to get that. Just a little familiarity with numbers. Okay, so we get B is approximately equal to 0.9. So where are we? Well, we're solving we just found that B is approximately 0.9. Plug this in to either one of equation 1 and 2. What do you get? Okay, so we got a good solution. Okay, now I didn't say before, but plug into the either equation and then solve for A, because most people manage to do that. Okay, so let's pick equation 1. Using equation 1, we get 60 equals A. And 60 equals A, B to the 8th, and we've found that B is 0.9. Now notice that we're rounding off. That really is like 0.904, 9036, something like that. If you're in open math and they're going to want 2 or 3 or 4 significant figures, you want to use 4 significant figures just to be safe. Although for this application, you're talking about a physiological response of a person in a situation, and there's a lot of uncertainty. Am I always having good days? and had a little bit of a cold and slacked off a little bit for 1 week. Okay, things like that make it kind of ridiculous to use more than just 0.9. But sometimes the software wants you to do that, even if it is ridiculous. Okay, so in reality, you're probably going to make judgments about how many significant figures to use. But to be safe with online homework, use plenty of significant figures. Doesn't have to be ridiculous. 4 should usually do it. Okay, so anyhow, we have this. 60 equals A times 0.9 to the 8th and 0.9 to the 8th. Now, if I was to, 0.9 squared is 0.81. 0.81 squared is about 0.65 or 66, probably 0.66. And 0.66 squared would be 4/9, which is 0.44. So I'm going to say it's 0.44. Now I get that if I square 9, I get 9 squared. If I square that, I get 9 squared squared, which is 9 to the 4th. If I square 9 to the 4th, I get 9 to the 8th. Just a little comment on how I do that. And the numbers are pretty good here. And I think that's pretty compatible with the numbers most people got in their calculators. So A is 60 divided by 0.44. Of course, 0.44 repeating would be 5, 2/3, 4/9. Should be like 9/4. And a fourth of 60 is 15. So that comes out about 135, which is in the range of numbers that people got. Okay. We now know A equals 135, B equals 0.44. So our model, y equals AB to the x, becomes y equals 135 multiplied by 0.44 to the x. Okay. Now, anytime you have 2 points, because remember what we did, we took the original situation, okay? We translated it so the asymptote of the exponential would be 0. Okay? In this situation, we expect that we're going to approach that 100% in some way, and it's going to approach the 100% exponentially. So that would be an inverted and vertically shifted exponential. We don't want to deal with inverting and vertically shifting it. So we translate the problem into a problem of how far we are below the 100% level. And we get this. And we expect that we're going to have an exponential model here. Might look something like this. In order to find the exponential model, we take the form of an exponential function. Y equals AB to the x is the easiest form to deal with algebraically. So we're going to use that form in this case, find A and B, and all we need is 2 points on the graph. Anytime you have 2 points on an exponential graph, you can use this form and find an exponential model. So if you have a situation where I've got this much money after 6 months and this much money after 14 months, you can take that information, represent it as 2 points on the graph, and do exactly what we did here. The numbers are going to be different. Hopefully, in the case of money, the numbers are going up instead of down here. And one more comment, just to review here, that down is good in the way we've translated this. Our first graph, where physical condition of 100% was at the top, okay, up was good. But now, how far below 100% we are, we want to be nothing below 100%. If we're 100% below, we're dead. Well, I've already said that. But again, this is the context for this particular model. Then the details are just pretty straightforward and they're pretty much the same, except you get different numbers. Procedure is pretty much exactly what we have here, but you've got to remember the rules for exponents. Okay? And you've got to apply them correctly. Now, to make sure it's applied correctly, we could check the solution. We should also, okay, well, our first equation came from the point 860. Our second equation came from the point 1240. Meaning if I plug 12 into this model that we just obtained and do the arithmetic, I should come out with something close to 40, shouldn't I? Okay, so we're going to test the model. I'll say we plug B into the equation from the point 840. I'll plug the point 1260 into the model. See what we get. Here, model is 135 times 4.44 to the x. Using 12 and 60, 60 is our y value. We get 60 equals 135 times 0.44 to the 12th. Okay. Now 0.44 to the 12th I think that I have my points wrong here. First point was not 840, it was 860. Our second point is 1240. Our first point was 860. Our second point was 1240. So we got to plug 1240 into the model, and we get 40 equals 135 times 0.44 to the 12th. And 0.44 to the 12th It's 0.44 to the eighth times 0.44 to the fourth. 0.44 to the fourth, according to my previous model, would be about 0.66 or 2/3. And this works out. Okay. Claim to be thinking okay. It doesn't mean I'm paying attention to the clerical stuff. B is not 0.44, B is 0.9. It's what we're going to get here with 0.44. It's not going to make any sense at all. This is 0.9 to the x, and that has never changed. So my 0.44s here should be 0.9s. Okay, and then 0.9 to the 12th ought to be about 2/3 of 0.44, which would be about 0.3. Okay, I'll just make a note. 0.9 to the 12th is about 0.3. And then 0.3 times 135. We get 40 equals 40.5. And this validates the model. Difference between the left side and the right-hand side is just due to the round off. Models validated to the extent that if the process is exponential, we ought to be able to make a pretty good prediction about how the recovery of this person is going to progress. Well, that's good. Now we can ask questions about the model. Okay. So the question is, when will the person be at 80%? Well, our model is how far down you are. Okay. So it tells how far down versus X. I should say Y equals how far down. %80 is down 20% from 100%. So we're going to find when Y equals 20. Okay. And that turns out to be pretty easy to do. Okay. Our model going to find when y equals 20. So we write 20 equals 135 times 0.9 to the x. And solve for x. Okay. Now let me ask you to take a couple of minutes and see if you can solve this for x. Okay, so I'm having a little trouble with this, but I think everybody pretty much knows how to do it. So let me just show how that would work. We want to put this into the form b to the x equals c. Okay. So what we're going to do is divide both sides by 135. Now I'm first going to write it 135 times 0.9 to the x equals 20. That'll put my x on the left-hand side, which is where we usually want to see it. And it's a little less confusing for most people. And we divide by 135, we get 0.9 the x equals 20 over 135. Okay, well, let's write that up here again. 0.9 the x equals 20 over 135. And see what we can do. Well, this is in the form b to the x equals c. If we convert to log form, we get log base 0.9 to 20 over 135 equals x. So x is a log of 20 over 135 divided by the log of 0.9. And now you can put that in your calculator. Okay, that seem familiar? Now I'm writing something down here, but just go ahead and work on this, and I'll just talk through this one real quickly. You get Okay, see how we did. Okay, everybody did pretty well with that. The only glitch I saw was somebody used log 0.9 of 20 over 135. Okay. In the log 0.9 of 20 over 135, just log of 20 over 135 over log of 0.9. Okay. So that equals what it equals. I'm thinking, let's see, we're trying to get to 20%. I'm not going to attempt to make a good estimate there, but work this out and it should work. Now, the other alternative, you have the equation 20 equals 135 times 0.9 to the x. You can take the log of both sides. You're going to get log of 20 equals a log of 135 times 0.9 to the x. Now, the log of 135 times 0.9 to the x is a log of 135 plus the log of 0.9 to the x. Just familiar multiplication to addition rule that I've already seen everybody having used in their homework correctly. So we have this. And now we just want to solve, first of all, isolate log of 0.9 to the x. Well, from this to this, log of 0.9 to the x is going to equal log of 20 minus a log of 135. Switch sides here. I get this. Log of 0.9 to the x is x times the log of 0.9. And now we got x down here where we can just use plain old algebra to solve it. So we have x log of 0.9 is log 20 minus log 135, which means that x is log 20 minus log 135 over the log of 0.9. That's going to give you exactly the same thing this does because look here, you got log of 20 over 135. That's just a log of 20 minus a log of 135 over the log of 0.9, which is just what we got when we took the log of both sides. Now we've learned to translate from exponential form to logarithmic form, which is the solution we used first. But I think you've also seen where you can take the log of both sides, which is always a valid step. Whether it gets you to a solution or not depends on what you're looking at. But for these equations, either approach can work. When you're translating between logarithmic and exponential form, though, be sure if you have an exponential equation that you put it in the b to the x equals c form. So if there's a number in front of your b to the x, you better divide both sides by that number or you won't have it in this form. Because this is the only form that translates to the logarithmic form, log b of c equals x. Okay? Okay. I think you're doing all right here. So see what you can do with the homework assignment.